Hello, everyone. Good afternoon. My name is Jonas Smedt from Ghent University. I am a PhD researcher and teaching assistant at the Faculty of Bioscience Engineering, and my research is about activated carbon, more specific, the chemical activation using molten salts. And in this research, I'll talk about the effect of pure zinc chloride and its eutectic mixture on the characteristics of Pinewood activated carbon. So I guess that you are all familiar with the concept of activated carbon and that it can be produced in several ways. And one method to obtain it is via chemical activation. In this process, you combine biomass with an oxidative chemical and thermally treat it by means of pyrolysis, and then you obtain afterwards activated carbon. The most commonly used oxidative chemicals are hydroxides, phosphoric acids, and zinc chlorides. And all of these chemicals actually have something in common, that they have a very low melting point, let's say roughly around 300 degrees Celsius, which means that they are in the liquid state when the conversion reaction takes place, and that you have then also good interaction with the carbon matrix itself. In literature, also often other chemicals are used. For example, sodium and potassium chloride. However, these have very high melting points, around 800 degrees Celsius. So if you want to have them in a liquid state and have a good interaction with the carbon matrix, you have to go above 800 degrees Celsius, which also exceeds the actual conversion reaction. But there's a solution for that. We can use eutectic mixtures. So in this, with this technique, you can combine different types of salts in specific ratios, and overall you obtain then a lower melting point. And the question is then, can we obtain such a mixture with these active compounds that melts before the actual conversion reaction starts? And there is such a mixture. For example, a 60-20-20 mole% mixture of zinc chloride, potassium and sodium chloride melts at 204 degrees Celsius, which means that we have an improved interaction with the carbon matrix with regard for potassium and sodium. We also have a very good heat transfer, and this mixture also has a low viscosity, which means that you can also penetrate the carbon matrix better and have an improved interaction. So in this research, we used Pinewood shavings and our eutectic mixture of zinc chloride, potassium, and sodium chloride. We physically mixed it in different salt to biomass ratios, starting from 0 to 1 as our control, so without salts, all the way up to 5, so 5 times the amount of salts compared to the amount of biomass. We activated it by means of slow pyrolysis at 3 different temperatures, 400, 500, and 600 degrees Celsius, for a period of 1 hour. After the reaction, we retrieved the solidified mixture of char and salt, and we washed it to remove all the salt from our matrix, from our carbon matrix in a diluted hydrochloric acid. We filtered the solution, and afterwards we obtained our activated carbon. So in this graph, you can see the effect of our salt to biomass ratio on the product yield of each applied temperature. So when we start at 400 degrees Celsius, we have a slight increase in the amount of char that is produced at a very low salt to biomass ratio. But when we increase the ratio again, it drops. And the inverse effect is observed with our liquids. But when you go higher in temperature, we can see that the amount of salt actually has a very significant effect on our product yield on our solid product yield. So the more salt we dose, the more char we get at 500 at 600 degrees Celsius. And again, the inverse effect on the liquid yield. So in general, we can state from that, in that regard, that these salts promote the formation of char over liquid. And there are several reasons for that. So we know that these salts lower the degradation temperature of cellulose and hemicellulose and benefiting the production of residual char. These salts also act as dehydrating agents, and especially zinc chloride, which also is a Lewis acid, so promoting the formation of water in our condensed liquid and also production of residual char. Potassium and sodium, on the other hand, promote the formation of char and non-condensable gases. And finally, we also assume that these salts can act as a diffusion barrier. Imagine if you have a biomass particle that is completely covered in liquid salt, then it would be very, or let's say, more difficult for the volatiles that come to existence during this conversion process to leave the system actually. So we have an increased residence time, and also these volatiles are then prone to secondary cracking. In the next two slides, I will talk about the non-condensable gases that we observed from these experiments. And the first thing that we noticed is the great increase in CO2 yields and the inverse effect on CO, so the lower yield of CO with the amount of salt that we dosed. And we attributed this to the fact that salts promote decarboxylation over the decarbonylation reactions. And sodium and potassium also favor decisions of linkages in pyranose rings. So that's why we get more CO2 and less CO. But there's also the fact that it's possible that we underestimated the yield of CO2, because these salts also can react with CO2 itself to form carbonate salts, which are then embedded in the solidified matrix. Next, we also noticed an increase in hydrogen with the amount of salt that was added. And we first thought, okay, this was governed by the water car shift, given also the trends that we saw with CO and CO2. But when we did some calculations, or just dove into the literature, we noticed that, okay, the temperature is way too low for that to happen. And we then found some articles, and they stated that the hydrogen production was generated due to the reaction between the ionic metals and the carboxyl and hydroxyl groups of your carbon matrix. Next to that, due to the secondary cracking and the increased residence time, higher carbons like C2, C3, C4 lowered in yield with the amount of salt that was added. And one interesting compound that we observed was chloromethane. And we noticed that the production of chloromethane actually increased with the amount of salt that was added, but drops with the amount of the applied temperature. So the highest production of chloromethane was at 400 degrees Celsius with a salt to biomass ratio of 5, and the lowest, and this lower than with the temperature that was applied with increased temperature. And the inverse effect was actually observed with our methane itself. So which means that there is some competition between one and another. And we know that methane is mainly produced via demethylation of the methoxyl groups that are present in lignin. And it's also from these groups that chloromethane comes to existence, because it's produced via a secondary nucleophilic substitution reaction between the chloride ion acting as a nucleophile and the methoxyl group, which acts as an electrophile. And is actually represented in the reaction scheme below. And then there's also the matter of temperature dependency. That we notice the highest yield of chloromethane at low temperature. You may think, okay, at higher temperatures, you have higher production of methane, so you should have more chloromethane. But due to the lower thermal stability of our chloromethane and its potential to react with hydrogen that's present in the environment, it tends to convert back, starting at a temperature of around 500 degrees Celsius to methane itself. So it wouldn't be a presentation activated carbon if you would not talk about the characteristics of our activated carbon. So first of all, we'll talk about the specific surface area. On the right-hand side, you can see three graphs. You have the representing the effect of the salts to biomass ratio on the specific surface area obtained for each applied temperature. And so on the top graph is the overall or the total specific surface area. Below that, the mesopores, and below that, that of the micropores. And we know that the overall surface area increases with the amount of salt that was added. And the most profound effect was applied at 400 degrees Celsius with a salt to biomass ratio of 5. There we had a specific surface area of 844 square meters per gram. And we also noticed something interesting is that we have a uniform effect regardless of the temperature. Is that when we start dosing our salts, so at a salt to biomass ratio of 1:1, we have at every temperature the same surface roughly, or actually a very similar surface area in the mesopores and in the micropores, and also logically then in the overall surface area. And the most limiting effect was observed at 500 degrees Celsius. There you can see from the micropore surface area that is, we have more or less a flat line around 600 without regard of the amount of salt was added. And we attributed this to the fact that the salts not also enhance the pore formation, but also block the pores. And when we are at 500 degrees Celsius, we had the most condensable liquids that are produced. And it can be difficult for these liquids to get released from the pores or to pass by these salts that are blocking them. And these can condense in the pores itself, reducing then the amount or limiting the development of our surface area. When looking at the pore size distribution, looking for my pen over here, okay. So when you look at the pore size distribution of 400 degrees Celsius with blue water control and then green ratio 1, yellow ratio 3, and red ratio 5, we see that especially in the micropores, the development of these pores is systematically enhanced. It also always increases a bit with the salt that is added. And also the same applies for our mesoporous area. So we notice that we have a steep increase in the larger micropores as well as in the larger mesopores. And this actually is a bit consistent for each applied temperature, so also for 500 and 600 degrees. But the development of, or let's say, the enhancement of the pores is different, because at 500 degrees, you can see that all the lines like yellow, green, and red of our different ratios in the micropores overlap. But then there's a small difference only in the larger mesopores regarding this, the amount of surface area that is produced. And then again, at 600 degrees, you have you start to get a difference again. So when you increase the amount of salts, you have again increased porosity. We also did some chemical adsorption with these activated carbons. So we determined the iodine number according to the ASTM. And we correlated this with the micropore surface area. We also did methylene blue adsorption. So we started off with a solution of 200 milligrams per liter of methylene blue. And we took from that solution 100 milliliters, and we dosed approximately 0.1 gram of our activated carbon. We let it absorb for 24 hours. And then we correlated it, the absorption, with the mesoporous surface area. And in both cases, we saw that we have actually a very nice correlation, or a very good correlation between the mesoporous surface area and the absorption. This can also state that in the future, if you want to do the same experiments, you get an estimation on the pore size distribution or the amount of which pores are produced, we can do this test very easily. So this was the first part of the research, and in summary for this, we noticed that we can produce actually activated carbon with a significant surface area at a low temperature, with a process that actually has a low energy requirement. The salts also develop the large micropores and the larger mesopores, and systematically, with increasing amount of salt, the same pores are enhanced. But then you can also ask yourself, okay, why do you use this eutectic mixture, and why don't you just use pure zinc chloride? Well, in the second part of the research, we made a comparison. So we started off from our optimal points, which we obtained in the first part. So 400 degrees Celsius, salt to biomass ratio 5. And then we compared it for the eutectic mixture. So we redid the tests in triplicates this time. We did also the same for pure zinc chloride. So we physically mixed it again. We also had our control, and then we activated it. This time we used a bit lower heating rate. We used 10 degrees Celsius per minute instead of 15. We washed everything afterwards in the same via the same mechanism, 0.1 molar solution of HCl. And we filtered it, and we retrieved our activated carbon, and we tried to recover also our salts. In this slide, presenting the product yields that we obtained from these experiments. And you can clearly see that the char yield increases when we use the eutectic mixture instead of the zinc chloride mixture. And we have an increase of at least 7% in that regard. So you know that the potassium and the sodium have actually a beneficial effect on the char production, on the yield at least. And again, the inverse effect, the liquid yield drops with the eutectic, attributed to the dehydration aspect and the of our zinc chloride. And the gas yields stayed pretty much the same. Looking then again at the non-condensable gases that we observed, hydrogen stayed pretty much the same between the zinc chloride and the eutectic, but interesting part is the CO2 and the CO again. So we have higher production of CO2 with our eutectic mixture compared to zinc chloride. And again, the inverse effect, higher CO production for zinc chloride and lower for our eutectic. And then also looking at the chloromethane production, we notice that we have a higher production of our chloromethane with regard to zinc chloride, attributed to the fact that there is more chlorine than present in the mixture, and which gives then more chloromethane. And this compared to our eutectic, which has a bit lower chloromethane production. So in order to characterize the quality of our activated carbons, we again did several tests. We have the FDIR elemental data, we have chemical adsorption and stuff like that. But today I will just show the specific surface area, the pores, and the pore size distribution, and then the iodine and methylene blue value. So we notice from the graph over here that actually the overall specific surface area presented in green, in the case for zinc chloride, is actually pretty much the same as for the eutectic mixture. You have a little bit higher production of our area, but it's actually the same. But the big difference lies in how the pores are formed and where the pores or the area, let's say, is formed. So in this graph again, in blue, we have the micropore surface area, and it is higher for our eutectic mixture compared to our pure zinc chloride. Also, this can also be noticed from our iodine number, which is higher for our eutectic compared to zinc chloride. And then the story turns a bit around for our zinc chloride and the mesopores, because there zinc chloride is the winner because it has a higher mesopore surface area compared to the eutectic mixture, and also has a higher methylene blue adsorption capacity. And the most interesting slides, in my opinion, from this presentation is this pore size distribution. where we have our three pore distributions of our control, our zinc chloride, and our eutectic mixture. And you can see from the larger micropores that the eutectic has a much better development compared to the zinc chloride. But then again, in the mesoporous surface area, the zinc chloride has a very broad range where it has area, where it has a surface area, compared to our eutectic mixture, which actually has in the big peak in the larger parts of our mesoporous area. So in conclusion, we can say that we have a low temperature, that we can actually create low temperature activated carbon. And that the eutectic mixture has very beneficial effects over the standard zinc chloride because we have higher yields. We also have higher surface area in our larger micropores, and we have a very narrow development. We have a good development over a very narrow range of mesopores in the larger parts compared to the very broad development in the of the mesopores in case of the pure zinc chloride, which can lead to the fact that we can look into adsorption, for example, of say, let's very large molecules such as pharmaceuticals, which is something that we want to do during the summer. Now for the future, indeed, as I already mentioned, we want to thoroughly investigate the absorption mechanism in both cases for zinc chloride and compare it to our eutectic mixture. We want to see if we are able to decently recover the salt, if it's in the same molar ratio as the original one, or etc., and if we can reuse it. We also want to check if it's possible to go to new to alternate feedstocks like food stones, for example. And then finally, some process optimization and looking for applications. I would like to thank my collaborators in this research, Pablo Arauzo and Przemysław Mazjarka, for all their knowledge and their aid in this research. And also I would like to thank my supervisor, Frederik Ronse, for the opportunity for the PhD. Thank you all for your attention. And if there are any questions, please shoot.
Thank you very much, Jonas. So Przemysław has a question, but I want to ask this first question before that, because he's your co-author. So have you looked at the so I was wondering about the yield increase, because you mentioned that one possibility might be the longer residence time and secondary char creation, probably. Have you checked the carbon yield and the carbon stability of your doped activated carbons? So the difference between the control. Between
the control and the eutectic mixture.
Yes. So
yes,
so
we have higher. I don't have the slide right here, but we have higher carbon contents. So what happens basically is when you let's say at 400 degrees Celsius, you apply your salt, you increase the amount of salt that are dosed. You will see that the amount of carbon, the carbon content increases, and oxygen and hydrogen drop. Okay, so also any chance you did an approximate analysis just for the stability? Because secondary char sometimes has the... We also do the approximate analysis. Okay. And also there's actually the same effect. So the carbon content there increases with the amount of salt that is dosed. Okay, thanks. Then let's go to Przemysław's question. Is there any assurance that the salts were removed entirely from the carbons? No. Okay. But it's not per se a bad thing, because there's a lot of stuff going on, and as you also probably know, in doping activated carbons with certain amount of chemicals. And let's say if you would have a carbon matrix which has zinc chloride, potassium, and sodium, it can be also a positive effect on it, because it can, for example, if you want to adsorb negatively charged chemicals, it can have a positive effect or aid in this adsorption.
Did you and you washed with hydrochloric acid?
Yes.
Okay, so any salt that is on there will probably stay on there for quite some time.
Well, it depends, because we noticed also that the ash content increases with the amount of salt that is dosed. We even did it with some tests. We even did it three times, and still the amount of salt is still the same. Keeps the same that's inside. So it's probably chemically bound or stuck into the pores. But yeah, that's something to look into the future.
And the follow-up, the same question from Przemysław, the second one. Would you suggest any method approach for the recovery of the salts that could be used for the process in a larger scale?
I would not go for water, but I would actually go for some organic solvents. Normally, methanol should work, which is something I also try to test during the summer. With methanol, it's easier to evaporate than, for example, water, and it also does not affect the carbon matrix as hydrochloric acid would.
And maybe also related to the upscaling possibility. You mentioned you used a 10 degree per minute heating rate.
Yes.
Do you know what happens if you go to industrial heating rates, like pretty high?
Yeah, and the industrial rates is pretty high. I have no idea what would happen to that. I think we a good question, and I'm not sure if I can answer it. But as you see, in the second part of the research, I used 10 degrees per minute, and in the first part, 15. In the second part, we had a higher surface area with 10 degrees Celsius per minute compared to the first part where we used 15 degrees Celsius. So I think that it would not be that beneficial, maybe. Yeah, but I can be wrong.
It might be interesting to check. Maybe something completely strange happens then.
Sorry?
So maybe something completely strange happens if you go up to 100 degrees per minute or something more close.
Yeah, it can also be that if the heat transfer is way too large, and the salts are actually mixture is stable up to a temperature of 400 degrees, but yeah, higher than that, the zinc chloride starts to evaporate. So in order to really have the same composition and reuse them, better to stay at 400 degrees, I would say, if you look into the terms of money.
Okay, great. Thank you, Jonas, for your presentation. Really interesting.
For the opportunity.
Eutectic mixtures. So that was our last presentation for this season. We will restart probably at the end of August with inviting speakers for the next series. So you will all receive this email at some point in the future. And the last thing from this season would be that I will send out a feedback form during the next week. So if you find 3-4 minutes to fill that out, I would be really grateful, because it will also help to shape which speakers to invite next season.